Hey guys, welcome back. Today, we are leaving the solid ground of observation behind and entering the realm of what-if physics. We're talking about ghost stars, objects that mathematics says must exist, but which we've never actually seen. Some are monsters from the dawn of the universe, others are so extreme they break our understanding of matter, and some represent the inevitable end of everything we know. We're going to do this chronologically. Let's start at the very beginning, back when the universe was young, wild, and extremely metal-poor. Part 1. The Monsters of the Primordial Age. Number 1. Population 3 stars. Imagine stars so pure that they consist of practically nothing but hydrogen and helium. No metals, no dust, nothing. These were the universe's very first factories. They were gigantic, hundreds of times the mass of the sun, and incredibly blue-hot. If you were even close to one of these, say, at the distance Earth is from the sun, you wouldn't just get a sunburn. The ultraviolet radiation was so intense, it would literally ionize your atoms apart before you could even blink. They burned through their fuel in a cosmic instant, blasting the seeds of life into the void. Without them, no Earth, no oxygen, no humans. But it gets bigger. Number 2. Dark stars. The name is deceptive. They weren't dark. They were likely the brightest objects to ever exist, powered by dark matter annihilation. But here is the weird part. These things were puffy giants. While our sun is dense, a dark star is like a ghost. You could technically fly a spaceship inside one for days without hitting a solid surface, just drifting through a glowing, superheated fog. And the scale is terrifying. They were so massive, they would swallow our entire solar system, appearing from the outside as a diffuse glowing cloud that outshines entire galaxies. The James Webb Space Telescope is hunting for them right now and might have already found some candidates. And if you thought that was extreme, here is number 3, Quasi-Stars. This is my personal nightmare favorite. Picture a star so massive that its core collapses under its own weight into a black hole. But, and here's the kicker, the star doesn't explode. The envelope is so thick it survives the collapse. It becomes a star with a black hole for a heart. The black hole eats the star from the inside out, generating enough energy to keep the outer layers inflated. It would shine with the brightness of a small galaxy, so if you looked up from a planet orbiting one, there would be no night, just a sky on fire. Let's take a second to breathe. How are you liking the video so far? If you're enjoying this journey into the unknown, do me a favor and hit that like button and subscribe. It really helps the channel grow. And hey, the universe is unfathomably vast. Maybe you know of a hypothetical star that is so bizarre it didn't even make it onto this list? If you do, write it in the comments below. I'd love to read about it. Now, let's get back to breaking the laws of physics. Part 2. Physics on the Edge of Madness. Okay, let's leave history behind. These are objects that could exist right now, but are so bizarre, they go against every intuition. Number 4. Quark stars. Take a neutron star, already the densest thing we know, and squeeze it even harder. The neutrons break down into a soup of free quarks. The surface would be metallic and incredibly shiny, but perfectly smooth. The gravity is so intense that the highest mountain possible would be less than a millimeter high. And if you touched it, you wouldn't just be crushed. The strange matter might infect your atoms, turning you into strange matter instantly. You wouldn't die. You would become part of the star's physics. And if we crank up the pressure even more? Number 5. Electroweak stars. Here, matter itself breaks down. We're talking about a core so dense that quarks are burned into leptons. This star wouldn't shine from nuclear fusion, but from burning elementary particles themselves. To give you a sense of scale, imagine something with the mass of 2 suns compressed into the size of an apple. The density is so off the charts that a single teaspoon of this star would weigh more than Earth's entire crust. But this exotic burning is just a brief last stand. It lasts for about 10 million years before the fuel runs out and gravity wins once and for all, collapsing the star into a black hole. Number 6. Boson stars. These are the ninjas of the stellar world. They aren't made of normal matter, known as fermions, but of bosons. The crazy thing is that they could be completely invisible, transparent. If you flew towards one, you wouldn't see a surface. You'd just see the background stars getting weirdly distorted by gravity, like looking through a funhouse mirror. You might fly right through it without hitting anything solid, though the tidal forces would feel unpleasant. These primordial ghosts likely formed in the earliest moments of the Big Bang and could survive indefinitely unless they accrete too much mass, at which point they instantly collapse into a supermassive black hole. It gets smaller. Number 7, Preon stars. If quarks aren't the smallest particles but are made of preons, then these stars could exist. Imagine the mass of a star compressed to the size of a golf ball. A golf ball as heavy as the sun. Visualizing the size difference to a sun is impossible because it's so small, but the gravity isn't. If you got close, the tidal forces would rip your atoms apart into a spaghetti stream of plasma long before you even saw the golf ball. Born from the crushing death of a quark star, they live a stable existence on the razor's edge of physics. But if they gain even a tiny bit more mass, they lose the fight against gravity and vanish into a black hole. Number 8, Thorne-Żytkow objects. This sounds like sci-fi, but it's a real theory by Kip Thorne. What happens if a red giant swallows a neutron star? The neutron star sinks to the center and churns the inside like a blender. From the outside, it looks like a normal, bright red giant. But inside, it's a cauldron producing elements like rubidium and molybdenum that have no business being there. It is a cosmic wolf in sheep's clothing. But this parasitic relationship doesn't last long. After maybe 1,000,000 years, a blink of an eye in cosmic terms, the neutron star core spirals into the center, triggering a supernova that leaves behind a black hole. Number 9, frozen stars. This is more of a historical concept. Back in the day, physicists thought time stopped at the edge of a black hole, freezing the image of falling matter forever. If this were true, you wouldn't look at a black void. You'd see a frozen, red-shifted graveyard of everything that ever fell in, plastered onto the surface like a cosmic sticker collection. Since time theoretically stops, these stars don't really have a lifespan or an end. They are simply trapped in the eternal moment of their own death. Number 10, Gravastars. But what if black holes don't exist at all? Instead of a singularity, you have a thin, ultra-hard shell of matter, and inside, vacuum energy, an anti-gravity bubble. There is no event horizon, so you could technically land on it. But since the surface is incredibly dense matter, hitting it would be like hitting an indestructible brick wall at light speed. Created during a stellar collapse that stops just short of a singularity, a gravastar could technically remain stable forever, acting as an eternal, dark tomb for the matter that formed it. Number 11, MECOs. Magnetospheric eternally collapsing objects. The star collapses, but the magnetic field is so strong it stops the collapse just before the end. Instead of a black hole, you'd have a glowing, rotating ball. But the magnetic field is the killer here. It's so strong, it would strip the iron atoms right out of your blood cells from light years away. Not a pleasant way to go. These form when a collapsing star spins so fast that centrifugal force fights gravity, but they live on borrowed time, surviving for perhaps thousands to millions of years. As they eventually slow down, gravity takes over and they inevitably collapse into a true black hole. Number 12, Planck Stars. Quantum physics hates singularities. When a star collapses, loop quantum gravity says, stop right there. At the smallest possible scale, the Planck scale, a repulsive force creates a bounce. Inside the event horizon, this bounce happens incredibly fast, literally in a few microseconds. But because gravity dilates time so severely, for us watching from the outside, that split-second bounce is stretched out over billions or even trillions of years. A black hole is essentially a star pressing pause on its own explosion. Theoretically, after eons of Hawking radiation weaken the trap, they might finally bounce back outward, exploding into the universe as a white hole. Number 13, Blitzars. A neutron star spinning so fast That centrifugal force saves it from collapsing into a black hole. But what happens when it slows down? One moment, there's a star. The next, literally milliseconds later, it vanishes into a black hole. But in that final moment, the magnetic field lines snap, releasing a fast radio burst, a cosmic scream of energy so bright it can be heard across the entire observable universe. These are born from supernovae that leave behind a hyper-rotating neutron star. They survive for 10,000 to 1,000,000 years, fighting gravity with spin until they slow down just enough for the inevitable snap. Okay, take a breath. We've survived the past and the extreme present. Part 3, the cold end of time. Now, let's look to the future. How does it all end? Number 14, blue dwarfs. Red dwarfs live almost forever, with lifespans stretching up to 10 trillion years. But just before they die, deep in the cosmic future, they get hotter. They turn blue. Imagine a sky filled not with yellow suns, but with tiny, intense blue dots. It's a beautiful, high-energy swan song before eternal darkness. The universe isn't even old enough for a single one of these stars to exist yet. We won't see the first one for at least 6 trillion years. We have to wait. Once they finally emerge, they will burn fiercely for several billion years before exhausting their hydrogen and shrinking down into white dwarfs. Number 15, black dwarfs. What happens to our sun in the end? It becomes a white dwarf, and then it cools down. Eventually, it's cold, a crystal of carbon drifting through space. But don't let the cold fool you. It's invisible, hiding in the dark. If you try to land on it, the gravity is still that of a sun compressed into Earth size. You'd be flattened into a monomolecular paste instantly. It's a dark, silent trap. It takes quadrillions of years for a white dwarf to cool down to this state. Once formed, they essentially last forever, unless protons themselves decay, in which case they will eventually evaporate into nothingness. And at the very end, awaits number 16, the iron star. In an unfathomably distant future, in 10 to the power of 1500 years, through quantum tunneling, all matter slowly transforms into iron-56, the most stable element. We are left with cold, perfect spheres of pure iron drifting through an absolute void. No light, no heat, no life. Just cold metal gravestones marking where stars used to be. That is the final state of the universe. But even they aren't immortal. Eventually, quantum tunneling will cause them to collapse into neutron stars, or black holes, restarting the cycle of darkness. Pretty grim, right? But also fascinating. Which of these stars would you want to see from a safe distance, of course? Let me know in the comments, and don't forget to subscribe so we can see each other again before we all turn into iron stars. See you next week.